Yeah, Come on, everyone. Let's start up. So, last thing we read was this century meter. Great. So, last thing we did was aeroplane wing, the Magnus effect. We have seen different applications also going from the wind tunnel, the ants to the aeroplane wing to the football ka banana shot, the blockage of the artery, a lot of stuff. So, going ahead with this, next thing that we have is a venturi meter. It's theoretical thing, but yeah, concept is important. Let's see what it is. So, what is the primary use of this? Did you ever think about this thing? In your house, you have this gas meter, right? When you use gas, every month we get a gas bill. We get electricity bill, gas bill. If you're in city like Delhi, you also get a water bill, right? Actually, even we don't get water bill per house, but every society gets a water bill, which actually they pay by maintenance and all. So the question is this: when you switch on the stove, right, and if you're switching on one stove, or if you're switching on the two stoves, right, how does the meter know how much gas are you consuming every second? So you should be billed based on how much gas you're consuming, isn't it? That means somehow we should be able to measure how much gas is being consumed every second, and from there we should be able to figure it out. So what we do is we actually use a kind of a venturi meter. We have two cases. We use a second case. So venturi meter, it is actually useful to measure volume flow per second. So case one, it's an open type. So let's say like this. So let's say we have a part of a pipe where the area changes, it becomes smaller, and then becomes to normal. So when the liquid is flowing through this, if you consider this point as one, if you consider this point as two, and if you actually look at the liquid level ka height here, if this is the height of the liquid level and this is the height of the liquid level, and let's say you measure it, sorry, that's H1, and if this is H2, can you tell me which one will be bigger, H1 or H2? Without any calculations, without anything, can you just see and tell which will be bigger? Again, ask yourself, where is the speed more, V1 or V2? So here the speed is V1, here the speed is V2. Where is the speed more? V2. If speed is more, what happens to the pressure? Last time we saw P plus half rho V square is constant. If speed is more, then the pressure is less. So at V2, the speed is more, so the pressure is less. If the pressure is less, then it pushes the liquid less height, na? You're getting it. So actually, there is a more height at point one compared to point two. Remember, if your velocity of the liquid flow is more, then the pressure in the surrounding region drops. So here let the pressure be P1 and here the pressure is P2, and let's say here the area is A1 and here the area is A2. Now remember, in this, I know A1, I know A2 because I can construct the pipe the way I want. I know H1 and I know H2. These things I can measure, isn't it? That's it. So I know only these four quantities, and using this, somehow I need to find with what, how much liquid is flowing through this pipe every second. So first one, equation of continuity, A1 V1 is equal to A2 V2. We use a standard things. Next thing, Bernoulli equation, P1 plus half rho V1 square is P2 plus half rho V2 square. Next thing, if you look at the height here, P1 is nothing but P naught plus rho GH. P2 is nothing but P naught plus rho GH2. The height in the vertical cylinder. Are the equations clear, everyone? So once you got the equations, substitute here. We end up with P naught rho GH1 plus half rho V1 square. This is P naught plus rho GH2 half rho V2 square. P naught goes off. Rho also goes off. This will be G H1 minus H2 is equal to half V2 square minus V1 square. V1 square is nothing but A2 square V2 square by A1 square. So from here we can get V2 is equal to 2G H1 minus H2 by 1 minus A2 square by A1 square ka root. Doesn't this kind of look like 2G delta H? Velocity of flux जैसा लग रहा है ना? We see this equation, it kind of looks like velocity of flux. 2G delta H by 1 minus A2 square by A1 square. Perfect. So I found the velocity. And what is the volume flow per second? Volume flow in a pipe per second is nothing but area into velocity. So A2 V2. Is this making sense, everyone? So if you have an underground river, heard about this river called Saraswati River? This river, right, doesn't exist on the surface anymore. It flows under the ground. Or similarly, right, you will actually find this water streams or something, under the ground. So imagine if you have a water stream like this, and let's say if you're digging a well, if you dig a well in this area, the water level will rise to, the higher level. If you dig a well in this area, the water level will be at a very low level, isn't it? So you have to put more effort to pump the water. So depending on which position you can dig a well, right, it matters. And similarly, this is the technique actually they use, whenever they're doing for oil or gas car exploration. They do dig some these mini wells, and from there they figure out, how much gas they can extract. Kabhi suna, Krishna Basin mein they found gas and it is estimated to be around 2 lakh cubic something, blah, blah, blah. They give an estimation. So this is a way to figure it out. Is this clear, everyone? It's not a tough one, but you should know the derivation also is there for HSE. It's also a concept. They'll give you numbers you have to substitute. So there, this is how you solve Bernoulli's equation, equation of continuity, and pressure, and you're done. But then again, this is not a ideal one. You don't want to have these open things on the top here to measure gas. So we have a second version of it, a closed type. That's what we actually use in the gas meter. Let me show you that. Is this clear, everyone? Turn in the page. Case 2, the closed type venturimeter. A manometer is connected. So we have it like this. Again, remember this is a part of a pipe. This is not a full pipe. So here we have a liquid or some gas is flowing through the pipe. Let this be Rowell. Here we have mercury. Let this height be H2. Let this height be H1. This is 0.1. This is 0.2. This is A2. This is A1. Velocity V1. Velocity V2. Pressure is P1. Pressure is P2. And from this center till this bottom, let this be height H. So how does this work actually? So think see again. I know A1 and A2 because from construction I can figure out what is A1 and A2. And here on the sides here, you actually have sensors. And mercury is a conducting liquid. So whenever the mercury touches the two sensors, the current will flow between them, right? And you will know how much height is. You're getting it? You can't go inside and see, no? But by looking at which sensors are activated, you can tell you what is the height of the mercury liquid on both the sides. So indirectly, you can find H1 and H2 from the sensors inside. You're getting it? Suppose inside if a gas is flowing, gas is a non-conductor. It won't let the electricity flow. But whenever the mercury touches sensors on both the sides, it becomes a conducting. Electricity passes through that. And then you know the sensors got activated. So indirectly, you know H1 and H2 inside this. Again, same story. I know A1, A2, I know H1, H2. And I want to find how much gas is flowing through this. First thing, equation of continuity. A1, V1 is A2, V2. Second is Bernoulli. Same equations, nothing changes. Half rho V1 square is P2 plus half rho V2 square. Next thing, if you consider this point here as A and this point here as B, we know pressure at A is equal to pressure at B because the same horizontal level, isn't it? The pressure inside the mercury at the same level must be same. But what is PA? PA is nothing but P1 plus rho liquid G. So that height is H minus H1 plus rho mercury GH1. PV is P2 plus rho liquid. So this difference in height, H minus H2 plus rho mercury GH2. This is your third equation. Please check the equations. If you got this, you're done actually. So if you substitute this, you will end up with P1. You will observe this H term actually cancels out. Rho mercury G rho mercury minus rho liquid GH1. Rho mercury minus rho liquid GH2. So P1 minus P2 will be rho mercury minus rho liquid G H2 minus H1. But I already know P1 minus P2 is nothing but half rho V2 square minus V1 square. I know mercury density, I know the gas density, and I know the difference in height from the sensors. So this can be written as V2 square, and V1 square is nothing but A2 square, V2 square by A1 square This will be 2G delta H rho mercury minus rho liquid by rho liquid. There. So from here I got V2 is 2G, the difference in height, rho Hg minus rho L by, yeah, it does look complicated, but by root. This is your velocity, everyone. There. So once you got A2, your job's done. How much gas is flowing every second? The volume per second is A2V2. There. I know the delta H from the sensors. I know the density of mercury. I know the density of the liquid. I know areas. You got everything. Look at the equations. I won't expect you to remember this result, but if it comes in the exam, you should know how to derive it. The derivation is important for HSC perspective. The result is important. It will be a direct question in the exam. Have a look at the steps. I used equation of continuity, Bernoulli, and I said pressure at A is equal to pressure at B. This is how your gas meter works. If you switch on the stove and if you switch on one stove, the heights will be different. If you switch on two stoves, heights will be different. So depending on how much gas you're consuming, the speed will change, and because of that, the heights will be different. So your sensors will be activated in a different way inside the gas meter. Is this making sense, everyone? So next time when you think about, right, how does my gas meter know how much gas I'm using? Yeah, this is what is happening. Any doubts on this? Quite a practical thing. Next one. Next thing. Siphon. This is also another application of it. The simple one. Did you ever steal petrol from a bike? Okay, let's not steal, but did you ever take out petrol from a bike? How do you do that? Because if you see a bike or something, right, the petrol tank is here. Now, how do you take it out? If you have these old bikes, right, they actually have a small pipeline here going into the bike. You can remove this and take it out. But now that is not there. Now the pipes are actually inside. You can't remove the pipe like that. So the only way to do is open the cap, put a pipe inside here, right? You pull the air out, and this oil just starts coming out. The simple example is this one. Went to the barber shop that you have that sprayer thing. When you do that, that's actually kind of something similar. So how does this work exactly? See, idea is simple. So if you have a container filled with liquid, when I was in fourth or fifth standard time now, in our house, right, we used to get water only one every day, like 1 hour in the morning. So we have to fill up the drums and have to use the water throughout the day. Now the drums used to be big. I used to be in fourth or third standard. I don't remember. I used to be small. So now I can't take a bucket, literally put it in the drum and pull out the water. I didn't have enough strength. So what I used to do, right? We used to have a pipe here. So for me, for my sister, this is how we used to take the water from the thing. So we used to have a pipe here. So put the pipe inside, a little bigger one. So put the mouth here and suck the air out. So what you're doing is once you remove all the air from inside, this thing creates a partial vacuum. So this becomes a low pressure region, and here it's a high pressure region. So the air pushes the liquid here, and the liquid will start getting into the pipe, and the water comes out from here. I used to put my bucket and fill it up. You getting the logic? Kind of concept is that. So you need to pull the air out and create a partial vacuum, reduce the pressure, so that the liquid can come out. So one day, I accidentally, right, I after taking the water, I forgot to put the pipe back inside. I left it like this and went away. All the water came out. The entire drum became empty. You can literally empty the entire drum. Then my mom started beating me with a stick. That's a different story. But again, you have to be careful. So how does this work? So we put a pipe here. So we define three heights here. This is H1. This is H2. This is H3. This is 0.1 and this is 0.2. So here H1 is the height of the liquid surface in the container. Here from the reference. H2 is the height of the opening. H3 is the maximum height of the siphon. So 0.1 is on the surface. 0.2 is just outside the opening. Therefore, P1 is equal to P2 is equal to P naught atmosphere pressure. Now, when you apply Bernoulli equation from 1, so the liquid flows. This is a streamline. Now, it kind of looks like counterintuitive, like, why the hell the liquid is going up and coming down? Now, there is no energy, law of energy conservation is still valid. Think about it. Look at this height here. The liquid from here is coming out from here. So, indirectly, can you see there's a difference in height? The liquid is going from a higher height to a lower height. So the final liquid will have less potential energy than the initial potential energy. But the problem, you have to take the liquid to a higher height. In chemistry, we call this thing activation energy. If this is your energy of the reactants and if this is the energy of the products, then why doesn't the reaction happen automatically? The paper you're writing on is actually more stable when it is burned down to carbon dioxide and ash. Ash and carbon dioxide is more stable than your paper. Then why doesn't the paper just burn automatically on its own and become carbon dioxide and ash? That is because you have to provide some energy called activation energy. I think for wood, it is around 800 degrees. So if you give that much temperature, you have enough energy to climb this peak. After that, automatically the reaction will proceed. You get more stable elements. The same way why we humans just don't burn automatically on our own, even though the ash and carbon dioxide are more stable. Our ignition temperatures are around 1600 degrees. Did you hear the term this activation energy? So here, pulling the air out from the pipe is like providing an activation energy to pull the water up. If you can take the water till here and after that it automatically starts flowing. So initially you have to provide some energy to pull the water out, and after that it flows automatically. So we'll apply Bernoulli between 1 and 2. So the Bernoulli will be P1 plus rho GH1 plus half rho V1 square, P2 rho GH2 plus half rho V2 square. This we are going to neglect since that area is much greater. The V1 will tend to 0. The siphon ka thing is small, so P1 is P naught rho GH1 P naught rho GH2 plus half rho V2 square. So we get V2 is equal to root over 2G H1 minus H2. Meaning result is pretty straightforward. Can you see? It kind of looks like root 2 GH. It's like a particle thrown from a height of H1 to H2. So as long as H1 is greater than H2, that is if the height of the water level is more than height of the exit, water will keep coming out. So you can actually drain the entire container, right? As long as you keep the pipe below the water surface. So idea is pretty simple. It's not a big result or something. It just looks like a particle freely falling. So now here, if I consider one more point here, 3. If you apply Bernoulli between 1 and 2 and 3, So you will notice P2 plus rho g H2 plus half rho V2 square. So here V2 is equal to V3 since the area is same. It's the same siphon. So this is P0 plus rho g H2 P3 plus rho g H3. So from here we get P3 will be P0 minus rho g H3 minus H2. Now tell me one thing, can pressure ever become negative? Yeah, sucking the air out is like kind of an actuation energy, right? Pressure should be always greater than equal to 0. Therefore, from here we'll get H3 minus H2 must be always less than equal to P0 by rho g. Now if you consider water, this thing comes out to around 10 meters. That means if the maximum height of the siphon from the opening is more than 10 meters, siphon won't work. Why is that happening? This, you have to go back to the barometer. Do you guys remember this result? If you create vacuum on the top, the height of the water level will be 10 meters. Meaning, even if you create perfect vacuum, you can't pull the water more than 10 meters. For example, dekho, let's say someone accidentally kept a siphon like this. And let's say this height is 15 meters. Now, let's say you pulled out all the air and you created vacuum here. Tell me what will be the water level maximum it can rise? 10 meter, na? So it won't even reach till the top. So pani bahar aayega nahi. Are you getting the point? So for a siphon to work, you can't have this maximum height more than 10 meters. Technically, in real life, you can't even have more than 5 meters. Because as the pressure decreases here, the water starts boiling and the whole thing is filled with vapor. Things actually get messed up. It doesn't work that way. You can't pull out a matlab. If you actually use a straw, right? Let's say if you're using a straw which is 2 meters long, and if you try to drink water, you really have to put a lot of pressure. Because you can't create a vacuum in your mouth, na? Getting it? So your straw actually works like this. When you're pulling the air out, you create a low pressure region in your mouth and the water gets through the pipe. So if you take a 2 meter straw and try to drink water, you will realize what I'm saying. If you can really pull out water, you really have strong lungs. Your cheeks will be hurt. Or maximum times you won't be able to pull out the water also. It will rise half meter or something and you're done. So siphon ka, this is one more thing. So that actuation energy should not be so high that you can't provide it. So the same reason, did you ever see this boring wells, that hand pump wala? So these hand pumps won't work for more than like 6-7 meters. That is the reason whenever there's a drought, these hand borings are the first ones to dry out. That's it. So these are two things in siphon. The speed of the liquid will be root 2 g delta h, the difference in height. Second thing, siphon won't work if the difference in height is more than 10 meters for water. Clear, everyone? Yeah, these are the two concepts we had. One is a venturimeter, quite useful to measure the flow of the gas, how much volume is flowing on. Second thing is your siphon. It's useful, without using any external sources, you can pull out the water automatically. So this is how it would look.
Flow from lab number 4. There's a water flow from left to
You can see how the pipe is. The area is big and the area becomes small and the area becomes big. At the top, you have this vertical, pipes having
right.
water.
Plexiglass, they gradually positive flow.
And those are called
From
piezometers.
left to right.
There, this
So
is
on
the
the
setup.
left-hand side, there's this blue.
So on the left-hand side, the blue one is a water tank. The water will flow from the bottom. On the right-hand side, you can see there are 7 pipes. So when the liquid flows through them, you'll have different water levels. You can see that from the picture actually. Did you see that? The area when it is small, speed is more, so pressure is less, and height of the liquid is less. This is what we did the first case, open type.
Water continually up here.
Let me show you the experiment when he does that.
I'm going to show
There, look at this thing.
Next, I'm going to show a short video presentation, a Venturi flow meter. This video for this. Before I start the video through the Venturi at the moment, this valve over here is closed.
The right side valve you can see, that is how you can start the flow or open the flow, or you can obstruct the flow.
And so all of the piezometers here have fluid at the same height. They would be at equilibrium with the fluid in the tank, and so that represents the fluid level in the tank at the.
So initially, since there is no liquid flow, they have same pressure, so the heights are same. And what he's saying is, since it is in equilibrium, the height of the liquid in the blue tank also must be the same, isn't it? So this is a case when the liquid is not flowing. Now, if you open the water tap, see what happens.
So now let's just watch the video. So at the beginning here, I'm just opening that valve to let some flow through, and you'll notice the piezometer levels changing dramatically.
There, this is what I was saying. You don't get the same heights. You can see that center one is actually the least, and the left and right, they are a little higher because the area is more, velocity is less, and the pressure is more. Is this clear, everyone? This is the Venturi meter which I was saying about. Clear with this, everyone? Getting it? So yeah, it does happen. This is not our just imagination. Then, if you look at a siphon,
working siphon. Unaided by any machine, liquid is moving through a hose from one container to another. The forces driving this process are complex and interesting. Let's investigate. Start by sitting a cup full of water on a block and an empty cup on the table. Position a hose so that it connects both cups. I colored the water to make it easier to follow this process. To start the siphon, we need to fill the hose with liquid. The hose.
So instead of using mouth, right, he's using this pipette there.
Squeezing the bulb forces air out of the tube, creating bubbles. Slowly.
That means now there is no air in the pipette, so it is actually a low pressure region because all the air is pushed out.
Releasing the bulb, we see liquid moving into the tube. We might say that the pipette is sucking liquid into the tube. Actually, the liquid is being pushed into the tube by the external air pressure. When we released the bulb, a partial vacuum appeared. External air pressure pushes water toward this vacuum. To start the siphon, remove the pipette while holding the end of the tube below the level of the liquid. It is important to keep this end of the tube below the liquid level, or the liquid will run back into the upper cup.
So what he's saying is this should be below the upper liquid. So H1 is greater than H2. You need to keep a difference in height or else the liquid won't flow.
Once started, the liquid will continue to flow. One of the surprising things about this is that the liquid actually flows uphill as it exits the upper cup. This process requires both air pressure and gravity.
Now see here, what is H1 and H2? H1 and H2 is the height of the liquid level from the ground, isn't it? H1 and H2 are the heights from the ground level. When both the heights are becoming almost same, you can see the liquid is actually slowing down.
If we look at the siphon in its start position, we see that the column of liquid in the tube on the left is much shorter than the column of liquid in the tube on the right.
So he's saying we can also argue this within terms of forces. So imagine this is like a chain, right? He's saying the red part of the chain has more weight component than the yellow part. So that is actually pulling the water from left to right. It's like a chain on a hemisphere.
The column of liquid on the pole towards the lower. One of two things happen. This siphon has stopped flowing. Equilibrium has been reached.
See, heights have become same.
The
H1 is equal to
in each
H2.
cup. When the siphon starts, the long column of liquid weighs more than the short column.
Now, see, if I take this and put it down,
Sitting both cups on the tabletop, we can
now
see
that
the
H2 is
siphon
more than
starting to
H1.
flow, stopping when both cups are at the same level.
Water flows from right to left. Again, it'll flow till it becomes same.
There is another question. Why does the column of water state in two directions? If you're with siphon,
So there you can
siphon each section of the
look at this
siphon
thing.
in
This is a good one. Multiple siphons. Kept a siphon from the 1 to second cup. Put one more from second to third. Put one more from third to fourth. There, so you can just continuously keep pumping the water. You can see the last cup is filling up. The second and
You'll
third
find
remain
more
constant because
science-related
inflow is equal to
activities and
outflow.
videos at our website.
Is that making sense, anyone? There, that is how you can remove liquid from there without using any mechanical things and stuff. All you need is a difference in air pressure, and there you get free petrol from bikes. We used to do that from our friend ka dad ka bike. So we used to have two bikes, no petrol. So sometimes what we used to do, we used to take out the petrol from my friend ka dad. We used to remove like what, 2 liters or something. Then put 1 liter in one bike, 1 liter in another bike, and then we used to roam around. His dad is an inspector, inspector of police, right? After evening or something, when the guy, his father is going out, the bike used to stop, and his father was like, "Bloody, में तो petrol तो कल ही डाला था." अरे यार, we used to get so much scoldings now. He used to scold me also. Arun, why are you going with these idiots and and you're spoiling yourself? My son is an idiot. Don't roam with him. अलग ही level scolding था. And they all used to look at me. And like, bloody, you are the one who gave us the idea, karke. So happens, right? You can portray yourself as innocent. Happens a lot. Happens, huh? In the house also. Your sister beats you, eats all the chocolates, and then cries, and mom comes and shouts on you. If you are the elder one, you will know what I'm saying. But if you are the younger one, then yeah. So that's about fluid mechanics. Like I said, the two concepts, one was venturimeter and one was siphon. The next one is viscosity. So viscosity is like what? Now, what if there is a friction or there is some kind of an opposition between the liquid layers? So we can't use Bernoulli now because energy is dissipated. It's a small chapter. The thing with the chapter, right? Either the question is easy or it is tough. It's like there's nothing in the middle types. You have pretty good ones based on integration though. But let's see. So what's viscosity? It's a small chapter. We will wrap up by next class. There is an opposition to the relative motion between the layers of the fluid. So when the fluid is flowing, right, there is an opposition between each layer. So just like friction, actually, if you see, there is an opposition to the relative motion between two surfaces. So this property is called viscosity. And the force responsible is called viscous force. So for liquids and gases, we call it viscous force. In case of solids, we call this friction. So fundamentally, they're kind of similar, but yeah, the mathematical formulations are different. In solids, this is friction. So whenever you think of viscosity, think of friction in terms of solids. Now, unlike friction, right, which depended only on the mu-ka value, nature of the surface, viscosity depends on multiple things. One is the temperature. So if you increase the temperature, this was a mains question. If you increase the temperature, what will happen to viscosity of liquids and what will happen to viscosity of gases? So there are two questions like this. So if you see the viscosity of liquids, decrease. This will be good, assertion reason questions also. Now, why does it decrease? So whenever you're heating the liquid, the bond length will increase. So bond distance increases, which leads to decrease in molecular interaction. So if the forces between the molecules decrease, they'll interact less. Intermolecular forces. So this is the fundamental reason. So the liquid will flow actually more easily. That means hot water will flow more easily than cold water. So next time, think about it. When you actually get fever, your body temperature rises. Now see, fever is actually not, fever doesn't mean you're sick. Because you're sick, you got fever. You getting the difference? People think, अरे मुझे fever आ गया, temperature rise हो गया. No, your body is not keeping well. So the body, what it does, it increases the temperature of your body. Why do you think it does that? When you are not well, why do you get a fever or why do your temperature rises? I asked this someone and said, sir, if you increase the temperature, germs will die. There's someone said the same thing again. So when you get a fever, right, your temperature doesn't exceed like 40 degrees or something, isn't it? 40, 41. If your temperature reaches 43, your brain cells will die. So you're saying 40 degrees mein bacteria mar jayega. Then when we boil water or when we boil, milk, why do we pasteurize 100 degrees? Isn't it? That 40 degrees temperature will do nothing to bacteria. So what happens is when you increase the temperature, viscosity of the blood decreases. So the heart can pump the blood more easily. So it is actually a way to conserve energy in the system. So basically your body is trying to get all the energy from wherever possible temporarily to, boost your immunity. Getting that? So the same reason, if you're staying in the cold or something for long, right? The reason you fall sick is because your body takes away most of the energy to maintain your body temperature rather than for immunity. So you actually start falling sick. Did you ever observe this thing during winters? People fall, more sick. Two reasons. One, body temperature goes down, so you need to actually your immunity goes down because your body is focusing more on keeping you, warm. Second thing, because it is cold, most of us stay indoors. One person gets sick, everyone gets infected. So that is the reason we feel like, winters may people fall sick more. So viscosity of liquids decrease. But if you take gases actually increase. So hot gas flows slower than a cold gas. Again, reason. Now see, in case of gas molecules, right, molecules are already very far. Getting it? So there is no molecular interaction between gases. The problem is the other way around. Collision rate increases. Do you guys remember the collision rate KTG में किया था? Z. Root 2 pi sigma square NVV mean. So if you increase the temperature, the molecules will collide more with each other. So that means they'll interact more. So they get more interactions then. So molecular collision rate increases. So in case of gases, molecules are very far. So there is no meaning of molecular bond, distance and all. But collision rate increases. So molecular collision rate increases, which leads to more interactions. Yes. So this was a question which was asked before. So these are the questions you can get in bits and mains. If the temperature increases, there will be four options: viscosity of liquids and gases, both increase, both decrease, increase, decrease, decrease, increase. हो गया question. Clear with us? Now, if you try to bring a mathematical formulation to this, in this primarily we have three concepts. One is the Newton's law of viscosity, we have Poiseuille's equation, and Stokes' law. So the first one is Newton's law of viscosity. This guy is there everywhere. Sometimes I get a feeling maybe this guy is an alien or someone from the future must have come back and given him some HC Verma or something. And he just copied everything from there and kept Newton in front of everything. Is there damn everywhere. Newton's laws of motion, Newton's law of gravity, Newton's law of viscosity, Newton's law of cooling, Newton's corpuscular theory of light, right? Newton's Leibniz theorem, Newton's calculus. There is same Newton. It is the same Newton. Kidding it. So there. Yeah, that's what happens, when you don't have internet, Instagram, nothing. What you do? You just sit there and start making laws. So this is what would happen. You actually know the story, right? What happened with Newton that time? There was a pandemic. It's like a COVID that time. I think I told you this thing. The university was closed, and the university said, "Everyone, get out from here and go to your house. We don't want you to die here. You can die at your house. Getting it? Don't die here because it gives a bad reputation to the university." Right? So everyone get out from here and go to your houses. So Newton came back to the house. The place where he was staying, there are no apple trees. Apple trees don't grow in that area. So that story of that apple falling is bullshit. Right? It's like he saw the apple and suddenly got an inspiration that is just to inspire people. It doesn't work that way. This guy already had an idea about something. It took him months to figure out was about gravity and stuff. So he was in isolation. So there's nothing there to think, and he could focus his full energy on it. So Newton, right? If you see all his research, primary research, whatever he did, was all in his younger years. Once he crossed after 25 or something, he really didn't do anything meaningful or fruitful. If you actually write, after Newton died, they had an auction about all his papers and research. Jo bhi books tha, whatever he wrote, people made an auction. So the guy who brought it, right, was so disappointed. I think after 25, 26 of age, Newton, right, completely started focusing on alchemy. So alchemy is like their fundamental thing in alchemy, right, is to convert lead into gold. So Newton was more focused on working how to convert, metals into common metals into gold. So he was into all kinds of voodoo stuff, black magics. I don't think black magic, but alchemy. He was doing every damn thing other than science. So whatever science that he could do, he finished it in the beginning, and then I think he's chillax. He's like, यार अभी कुछ करना नहीं है. In the future, this Arun is going to scold me. करके I think he shifted to alchemy or something. So yeah, he didn't do anything meaningful after that. Then he went into stock market. He lost a lot of money. Then he also became a member of the parliament where he did nothing for 2 years. There was the only one recorded statement of Newton, like, in that entire 2 years of the parliament session, right? The one time he spoke, it seems, was he called the person beside him and said, "Can you please the window? Because cold air is coming in." That is the only time he spoke in the parliament, it seems, for 2 years. Obviously, he was not a political material, so he's just a honorary member of parliament, like a Sachin Tendulkar. He's also honorary member of parliament. He just goes there for time pass, but nothing happens fruitfully. No, he's a good cricketer, no doubt about it. That's it. Just because you're a good cricketer doesn't mean you become a decent politician. People don't realize that. Newton is a good scientist, but what is the point of making a member of parliament? That guy had no clue what the hell was happening. So this was a concept there. So if you take a plate of area A here, and let's say if this guy is going with velocity V, so you're dragging this plate on the liquid surface, and let the thickness of this thing be Z. So when you're dragging this plate, there will be a viscous force acting on the plate, which is actually slowing this down. Agreed? It's like if you drag a plate on the floor, there's a friction acting backward. So this force is given by F viscous. This is an experimentally derived. So eta A dV by dz. Let's see what each term means. That's your first formula there. You need to remember this. The negative sign indicates opposition. right? A is the area in contact with the liquid. So how much area you're touching. Now, if you observe, yeah, the last line is the ground or something. If you remember in friction, friction was independent of area in contact. Yeah, it depended only mu into n. It didn't depend how big the area was. But here it actually depends on area. The bigger the surface, more friction you get. Eta is coefficient of viscosity. Now this you have to be careful. If you look at the units of this eta, is poise. This is another scientist who worked on this viscous stuff. We will talk about that guy also. We have an equation on it. So poise is an CGS unit. This is not an SI unit. So this is a CGS unit. So what it means is 10 poise is one SI unit. That is the conversion factor. So you have to be careful in the exam if they give you, let's say someone gives you eta is 30 poise. So then we use eta is equal to 3 in calculations. Your seniors have goofed up this thing multiple times. They used to put 30 directly in the exam, and there should be two options, 0.1 and 1. Or 10 का difference आएगा. Clear? So if someone gives you eta is 30 poise, make sure to use eta is 3, not 630. And this quantity here, dv by dz, this is called velocity gradient. So basically it tells you how the velocity is changing per this thing, per unit length or unit depth. So for thin layers, we can write dv by dz is delta v by delta z, which is the relative velocity between two layers by distance between the two layers. I'll show an example. So it's like P2 minus V1 by Z2 minus Z1. Have a look at this page. So these are the two things you need to remember. Let's see. Let me show an example how this works. So let's say we got a plate here. Let's say the area is 2 meters square. And let's say the velocity is 2 meters per second. Let's say somewhere here, this layer is going with velocity half meter per second. So different layers will have different velocities. Let's say this is 2 centimeters. And let this be 3 centimeters. And eta is, let's say, 60 poise. Now, if they ask you find the viscous force, so first thing here, delta V by delta Z. So you choose any two layers, V2 minus V1 by Z2 minus Z1. So here one layer is this guy here. This is the 0.1. Let's say this is 0.2. This is 0.1. So V2 minus V1 will be 2 minus half, and the distance between the layers is 3 minus 2 centimeters. That will be 3 by 2, 300 by 2. So viscous force will be eta A. The minus sign indicates direction, so I will not write the thing. So eta is 6, area is 2, and this is 150. How much is this? 150 into 6, 1800 newtons. Is that making sense, everyone? Remember, this is valid for thin layers. So here it is in like 2 centimeters, so it is small. If the layers are thick, you can't use this. We have to figure out that function actually. We'll see a problem later on like that. For thick layers, dV by dz, you can't write v2 minus v1 by z2 minus z1. At a mains level, they won't ask for thick layers. Advanced, they will ask you as paragraphs. So here are a few points here. So when you write this equation, F is equal to eta A dV by dz. So what is this quantity? This F by area, is this equal to pressure? Force by area, is it pressure? What is pressure definition? Force perpendicular to the area, isn't it? But this force is parallel to area, na? This force is parallel to the surface. This is not pressure. So be careful. There is a different term for this. It's called shearing stress. We'll see later on. This is force perpendicular to the surface area. So be careful. Don't write that F by A as pressure. And another point here, this is kind of an assumption which actually holds. We assume, listen to this carefully, it's an important assumption. We assume the velocity of the liquid layer in contact with the solid has the same velocity as the solid. What do you mean by that? So it is saying if you have a layer which is touching a solid, it will have the same speed as a solid. Imagine ketchup bottle. When you turn the bottle and remove the ketchup, did you see how will the ketchup come out? Ketchup in the center will come out. Most of the ketchup is stuck to the walls, isn't it? Because the walls are at rest, the ketchup which is sticking to the walls is also at rest. You're getting it? Or if you ever notice this thing, when the river is flowing very fast, sometimes you'll see the fish, the crab, and everything, they're just walking happily at the bottom of the lake. Water on the top is flowing very fast, but at the bottom, nothing is disturbed. They are like chilled out. So whenever a river is flowing, you'll observe different layers will have different velocities. All the water in the river is not going at the same velocity. So if you actually try to see the velocity profile, this is how it looks. So if you look at the water in a river, if this is the ground, which is at rest, that means the liquid touching the ground will be at almost zero speed. So this thing will not move. The next layer will go a little faster. Next layer will go a little more faster. Next layer will go faster. This is how it will be. So this is how the velocity profile looks like. So the top part of the river is flowing the fastest, whereas the bottom layers are going like almost at a negligible speed. So whenever a fish wants to go down the river, it will swim on the surface. When the fish wants to go opposite to the river, it will swim at the bottom of the river. You're getting it? So this is how it will flow. So whenever a liquid flows, this is what will happen. So using this logic, can you tell me how will the water flow in a cylindrical pipe or a gas in a cylindrical pipe? neglect gravity, now these are the walls, isn't it? So this will be velocity 0. So this is what would happen. The liquid which is at the edges will be at rest. This is like the ketchup sticking to the walls. As you go to the center, the speed increases. You have maximum speed at the center. So in a pipe, the liquid flows fastest at the center. On the ketchup, when you turn the ketchup bottle, ketchup flows fastest at the center. The middle ketchup comes down first. Then again, speed decreases and becomes 0. So this shape is actually a parabola. So if you neglect gravity, or if you take a gas flowing through a pipe, this is how the gas flows. So we didn't do this in Bernoulli equation. There was no viscosity. All the liquid was flowing in the same rate. But if you have viscosity, this is what would happen. You have to prove it, Vihan. That is just your imagination. You have a proof for that, or you're just making one statement? dv by dz is linear. So cone, what kind of statement is that?
So no, like here in the first one, it was a line.
Where?
So in the water in a river one.
I don't know what is that. That's not a line. Who told you? That looks like a line. We don't know what it is. You have to know a lot of functions there. That is not a thin layer, right? A river is not a thin layer, God. If a river is a thin layer, you will not see anyone drowning in a river.
Yes.
Even in the river, the top view will be same as a cylindrical pipe. I don't know what you mean by that. You're saying edges, na? The left and right will flow slower. The center of the river will flow the fastest. Is that what you're saying? Yeah. So river mein actually there are two gradients. Left to right, up to down. Up to down mein up flows the fastest. Left to right mein middle flows the fastest. So the velocity profile in a river in 3-dimensional is different. And what I'm showing you is a side view. Is this thing clear? Now, if you think about it using this logic, in Tom and Jerry, there is an episode. The Tom takes a cigar, it smokes, and it releases rings. Anyone remember there's an episode like that? It's like you get rings like this. It releases rings, meaning if there is someone, people are smoking, right? Sometimes they do that. So what they actually do, right? The mouth, you think of like this. If your entire mouth is full of smoke and if you just blow it out, technically speaking, shouldn't you get a cylinder of smoke? But the edges of the smoke are flowing slower and the center is flowing faster. So from a cylinder, if you remove the center ka smoke, what do you get? A ring, isn't it? The center part of the disc is flowing faster. The edges are going slower because of the drag. So once the center leaves, what you'll find is a ring. So that is what Tom does in Tom and Jerry actually to get that rings. He's a physics genius. So how does that look like? It's also called as a vortex cannon. You can do this at home. No need to smoke. I won't recommend it also. It's a very bad habit. But how do you do this? You get a box from Amazon. That's easy. Just take your mommy phone and order something. You get a big box like this. And if you order a smaller item, they'll send a big box for no reason. Make a hole. Now, this thing, they're using dry ice. This is the fog machine they use in theaters. We don't have this machine, so you can use agarbattis. Take 4 or 5 agarbattis, put them inside, let the box be full with smoke. It works. I did that. There. Now, if you hit the box, smoke will come out of the hole. See that in slow motion. You saw that's a disc, right? Almost like a disc. It's flowing forward. Can you see the ring? Because the center part is going faster than the surrounding. The center part is like a hole and the edges are little still thick. What you saw is a ring. This is called a vortex cannon. I think in US and Europe, right? They're also trying to test this to use as a weapon. So you can have a high pressure air, and when there's a crowd or something to disperse, you can hit them with high pressure air, and they'll actually get blown off without killing anyone. But you can scare them like this. So this girl is busily building something. Happens a lot of times. Sister does something, brother comes like this, and boom. That's a vortex scanning. I can actually use a hair pressure to hit that thing. See. Nice, no? So that is how we can make one, but sometimes even the nature wants to make rings. This is a volcano making rings. Can you see the rings? Little rare, but does happen. Or you can also see here, a lot of the rings.
Oh, Toby, the finest weed in the South Valley.
This is physics. You got a ring? That is viscosity. This is magic. You get a ship. So to learn that, you need to find some other teacher. I can't teach you that.
Gandalf, my old friend.
So there. That is how you can see it even in a lot of the rings. So if you get a ring, it is viscosity. If you get a ship, then it is magic. Clear on this? So there. So that is a bit about it. So let's see some questions on this. There. I taught you only one formula till now, eta A, dV by dz. So you know force. And the rest of it kind of looks like mechanics. So first question. Let's say we have two surfaces. So we have two planks here. Let's say this upper plank is going with 3v. The lower plank is going with v. Imagine like this. Your ceiling on the top is going with 3v forward. Your floor is going with v backward. This entire space between these two plates is filled with liquid. Eta. So you kept a plate in the middle and you're pulling this with v by 2. You're pulling this with v by 2 there. Meaning, if I have to give an analogy, think of like this. If you have two bread ka slices and there's a cheese ka slice in the middle and you're pulling the cheese ka slice outside. Can you visualize that? Between two breads, there's a cheese ka slice and you're just pulling the slice out. So if you look at the side view, this is how it looks. This is going with 3v, this is going with v. This plank is somewhere here going with v by 2. This entire thing is filled with liquid. Viscosity eta. This is d by 3. This is 2d by 3. So now the thing is, this plank will not go on its own. You need to apply force because there is a viscosity. So someone is applying a force to drag this plank. So the first question, find the F external to pull out this plate with a speed v by 2. So if you want to pull this plank with a speed v by 2, you need to apply some force. How much is that? Second question. Suppose you don't want to apply the force. So where should I keep the plate? So there is a particular place if you keep this plate, it can go with v by 2 without applying force. Where should the plate be placed? Such that it moves with v by 2 without F external. Meaning the second statement of the question, say, I'll tell you what. If this is going with 3v, somewhere here you'll have 2v, somewhere you'll have v, somewhere you'll have v by 2, isn't it? Then you'll have v by 2 in the backward, and then this will go with v. So if you can keep the plate at v by 2, it will automatically go with the layer, isn't it? You need not apply any force. So every layer will have a different speeds. So you're putting this plate at a distance of d by 3 and you're dragging it out with v by 2. So how much force should you apply? This is the only formula you have, eta A dv by dz. Think for a minute, give it a try, then I'll show you the first one, then I'll give you some more time for the second one. How many frictions will be there? How many frictions will be there? Imagine the same thing again. If you have two bread slices and if you're pulling this, won't the upper slice and the lower slice, both of them apply friction? There are two surfaces, one on the top and one at the bottom. But what are the directions? Are they both left? Viscous force opposes what? Relative motion. It doesn't oppose your velocity. Let's see. Try. I'll give you a minute. Get the value. Fine. Then apply F in the backward direction. What is the problem? Velocity is constant. Yeah, what you're saying is true. It would have accelerated. So you need to oppose the thing. Should I help you with one? See. First of all, if you draw the FBD of this plate, look at the forces. Who is going faster? 3V or V by 2? 3V is going faster, right? So you should oppose the 3V and support the V by 2. So this viscous force will be forward. This is a mistake people do, everyone. Just because I said friction and viscous force, you think it is opposing you. Let me ask you this question. Let's say you got down from a train in a local station and you're walking with the crowd. If you walk faster than the crowd, what will the crowd do to you? They push you back. What if you walk slower than the crowd? The crowd will push you forward. What if you walk with the crowd? There's no force. Are you getting the thing here? So the viscous force is not opposite to your velocity. It depends on the relative velocity. If you walk slower than the crowd will actually push you forward. The viscous force is forward. You're getting it? So upper, the viscous force is F1 forward, and piche, the viscous force is F2 backward. Because this guy is going with V, this guy is going V by 2. You have to oppose both of them. If you remember, this kind of looks like friction between blocks. And this is your F external. Since it is going with constant velocity, F external plus F1 must be equal to F2. So this is F. What is F1? Eta area, relative velocity between the two layers, which is 3V minus V by 2 by distance between the layers, D by 3. F2 will be eta area, relative velocity is V by 2 minus of minus V by distance is 2D by 3. How much is this? 15 eta AV by D. That guy will be 3. So 9 eta AV by 4. So this is 9 by 4 minus 15 by 2. Multiply 2 to 30 minus 21 by 4. I am getting F is equal to minus 21 by 4 eta AV by D. The negative indicates force is not on the right hand side but on the backward side. Nahi Puroja, meaning of minus n is what? Minus n indicates opposition, isn't it? So you use the directions, right? By here. So you don't put minus n again. The minus n is telling you the direction is this way. Done. Minus n is used up. Just get the magnitude.
But sir,
Sure.
the minus sign indicates that it's going in the direction opposite to that of
Relative velocity, right? ठीक है ना?
Yes.
So v by 2 minus 3, v का minus of minus ना?
Got it.
अगर mathematically करना है तो, yeah. Distance of 5 by 2d from upper wall. क्या बोल रहे विहान? It's d by 3 and 2d by 3. Where did you get 5d by 4 from? Have a look at this, everyone. Question still not over. If you want to put the plate here and pull it with v by 2, itna force apply करना पड़ेगा. Now the second part of the question. Where should I keep the plate so that I don't want to apply any force? there is one particular position. If you keep the plate there without applying any force, the plate will move with V by 2. Okay, are you saying the answer for the second part? Yeah. But still, you got 5D by 4, means you are out of the system. I don't know where you are. That's right. Second part of the question, everyone. Where should I keep the plate so that you don't need F external force? Matlab F1 is equal to F2 now. Try. You got a minute. Hmm. 5D by 8. 30 seconds more. Get it? You have two right answers. Poroja and Vihan. Yeah, 5D by 8 from the top. Same thing. If you draw the FPD, let this distances be x and let this distance be d minus x. Acceleration is 0. So you want F1 is equal to F2. So this is eta A, relative velocity is 3v minus v by 2 by x. This is eta A, 3v by 2 by d minus x. Eta A we will cancel. This is 5 by 2x. This is 3 by 2d minus x. 2 also will cancel. You'll end up with x is equal to 5d by 8. Easy? So if you put at this point, the layer is actually going with v by 2. And you're also going with v by 2. There's no need to apply any one force. Clear, Devika? Got this? Yeah, let's focus. Any doubts on this? Devansh? Clear? Nikhil? Got this? Adi? Sure? Ansh? Clear? Arnav? Arush? Any doubts on this? Vignajit? Sharman? Soham? Ojas? क्या हो गया? Ojas not keeping well. You're having fever. No. You just woke up from sleep. Happens. Next one. We have a long incline. So long incline meaning you can treat it to be infinity. On this long incline, you have a thin layer of fluid. Thickness Z. So if it's a thin layer, you can use V2 minus V1 by Z2 minus V1. Thickness Z and viscosity is eta. Now what you did, you kept a plank on top of this. This is a plank of mass M and area A. Released from rest. So what will happen? This plank will start sliding on the incline. You must have gone to this water park, na? On that sledge, what they do? They put the rubber sheet. There is a water flowing here, and then you glide on that. Did you ever try gliding without that water? And did you ever try to go without that rubber sheet? Never do that. Getting it? Without the rubber sheet, if you jump onto that plastic, unfortunately, if there is water, what happens is the water is not uniformly spread. At that speed, if your skin touches the plastic below, right, your skin will just tear off. ज़्यादा नहीं है, but did you ever got skin burns or something when you rub against something? The upper layer just goes off. It burns really bad. Getting it? So you should be on that rubber sheet. And there should be water below there, because if there's no water, you won't slide properly. You'll get stuck somewhere in the middle, or you'll get that friction burns. So that's a very bad thing. Be careful. So if you release this from rest, first question, find the velocity as function of time t. Find the velocity at time t. Plot Vt graph, acceleration time graph, velocity exposition time graph, acceleration velocity graph. 4 graphs, everyone. This would be a good paragraph question or a more than one choice. So we have a long incline, gravity is there. So the mg sine theta is dragging you down. Viscous force will act you back. So something happens. So find the velocity of this plank after time t and plot Vt graph, At graph, Xt graph, and acceleration velocity graph. 4 graphs. If this is a paragraph, I would ask you velocity and I'll ask you Xt graph. Or I can also ask in matrix matching also, graphs. Try. I'll give you 2 minutes. Think about it. Most of it is max. Physics part is actually easy. Try. Think about it. I'll give you a minute or two. Then I'll show you the equation. Then I'll give you another minute to solve. Just give it a try and let some water and come. Yeah, see now what you got. Suppose अगर ये question exam में आएगा and guess करना है. How do you guess? If you put t0, क्या आना चाहिए आंसर में? T0 should give you 0. Is it giving? हूँ क्या रे? तो 1 plus लिखा वहीं पे. 0 कहाँ से आ रहा है? You're getting 1 plus 1 आ रहा है ना वो. E power 0 is not 0. E power 0 is 1. Now see, one thing you can now actually kind of have a guess from here. Look at this thing. So initial mg sin theta is pulling you down, viscous force is up. Agreed? Viscous force depends on velocity. What is your initial velocity? 0. So viscous force is 0, mg sin theta is strong. So niche jayega. Now as it is going down faster and faster, viscous force also will increase. At some point, you will go so fast, your viscous force will become equal to mg sin theta. At that point, your velocity becomes constant. Making sense? So eventually, you will have a constant velocity. Velocity can't keep increasing forever. So let's try to see this mathematically. So these kind of functions, you'll get an exponential generally. So we have a Planck here. This is mg sin theta. This is viscous force. I'll just call it Fv. And acceleration. Now, if you look at the Planck here, what are the 2 points we're talking about? This is going with V. This is V0. This is the thickness of that layer there. So dV by dz will be V minus 0 by z minus 0, which is V by z. So F viscous, again, we'll not take the minus sign. The minus sign already gives the direction. So eta A V by z. This is your viscous force. Yeah, you get a terminal velocity. So this will be mg sin theta minus F viscous is equal to ma. This will be mg sin theta. Viscous force will be eta A V by z is equal to mdv by dt. So this will be dv by dt. Send m that side. We will get g sin theta minus eta A V by mz. For convenience, what will I do? dv by dt. Let's write it as a plus bv. A is g sin theta. B is eta A by mz. So you have dv by bv plus A is equal to dt. Integrate on both sides. This will go from 0 to v and 0 to t. I hope everyone remembers integration for this. This is 1 by b ln bv plus A. Limits will go from 0 to v. This is time. This will be ln bv plus A minus ln A is equal to bt. This will be bv by A plus 1 is equal to e power bt. So you get v is equal to A by b into 1 e power bt minus 1. Substitute the values again. So A by b will be mg sin theta z. The minus sign will be there, that I'll push it inside. Eta A 1 minus e power minus eta A time by mz. There, that's your velocity as function of time, everyone. It's an exponential one, as expected. Like I said, once you have written this equation, physics got over here. So what comes after that is just max. That is okay, you'll be able to handle that. Now, if it is a simple mains level question, they'll ask you find the final velocity. So you can clearly see here at t tends to infinity, the velocity becomes v terminal. The final velocity is mg sin theta z by eta A. Now, if they ask you in the exam, find the terminal velocity, you need not do this much. But have a look at this. I'll show you how to do that. You can find the terminal velocity much easier in one step. Yeah. Now again, look at the word terminal velocity, meaning your velocity became constant. Means what? Your acceleration is 0. So to find terminal velocity, so we have mg sin theta minus F viscous is ma. So for we find v terminal, we can see v is constant. So eventually reach a constant velocity. Therefore, acceleration is 0. We get mg sine theta is equal to eta a v terminal by z. So v terminal is mg sine theta z by eta a. There, one step you'll get an answer. Is that clear, everyone? Now, how to draw the graphs? How does a VT graph look like? Now look at this. We said your final velocity is constant, V terminal. But when will you reach V terminal? Infinity pe na? Matlab you will never reach. So you'll start from 0. You will get closer and closer and closer to this line, but you'll never touch the line. Making sense? That's how a VT graph looks like. An increasing velocity, but it's getting closer and closer to that line, but you'll never reach that line. How does an AT graph look like? Your initial acceleration is g sine theta. There's no viscous force, then it decreases, decreases, decreases. You will tend to 0, but you'll never be 0. Because at infinity, your acceleration is 0. So it will be a decaying function there. How will an XT graph look like? That is the most interesting one. Can you try XT graph? I'll give 30-40 seconds. If that's VT and this is AT, can you draw XT? Right, we have. Can you tell me the straight line ka slope? Let's see. So initially your position is 0. Think about it. In an XT graph, what is slope? In a position time graph, slope is velocity. Agreed? So initially velocity is increasing, so आपका slope भी increase होगा, increase होगा, increase होगा. But infinity में your velocity becomes constant. Means in an XT graph, the line should be a constant line. This is theta, so tan theta is V terminal. So your XT graph will keep increasing, increasing, increasing. It will get closer and closer to this line, but it will never touch. At infinity, it becomes a straight line. Is that making sense? You will never cross that green line. At infinity, your graph becomes a line. AB graph is the most easiest one. You can clearly see from this equation. Mg sine theta minus eta v is equal to ma. This looks like y is equal to mx plus c. It's a straight line. This is B terminal. This is g sine theta. There, the 4 graphs. Check it out. It's a good question. Is this clear, everyone? Let's see one more. Any doubts on this, Ahna, Daksha? Clear? Devika, Ishana, Jainil, Adi? Clear? Puruja? Next one. We have a disk here. Mass M, radius R. This is rotating with omega naught. And here we have a thin layer of oil or a fluid or something like this. This is a thin layer Z, viscosity eta. So a rotating disk is placed on a thin layer of fluid. Remember where we seen this question? Anyone remember? We have done something like this before. A rotating disk is placed on a thin layer of a fluid. So we know the disk will slow down because of the viscosity. Find omega as function of time t. So if initial angular velocity is omega naught, find angular velocity after time t. Now, did you remember this question where you have seen? Anyone remember where you have seen this? Where? याद आया? A rotating disk is placed on a rough floor. Find the time when the disk stops rotating. This is what I keep telling you. You don't learn new things every time. I know it's not the exact problem, but you know how to choose an element. What did we do? The concepts are still same. If you think every problem is a new one, you will be overwhelmed with the number of problems. This is how you should think. This is not the solution, but this gives you a lot of ideas on how to proceed with this problem. Did you see what we did? We took an element, friction is clockwise. There is a torque on each ring. Then we calculate the torque on the total disk. Then we did I alpha. We did a lot of things. Have a look at this. The idea was the same. Now can you try this thing? Try. I'll give you 3 minutes. Omega naught minus. There, man, you goofed up big time. Did you even do integration? You got the answer without integration. Did you use double integration? You have to integrate 2 times. That you didn't do, I'm sure. Is alpha constant? Then why the hell are you using the common equations, God? Huh? Look at the first step, everyone. So we have the disk here. At a distance x from here, we choose a thin ring. Thickness dx. So on this disk, if you take this thin ring, the velocity of this thing is x omega. Now be careful, you're comparing this with what? With the ground. So this point here, velocity is 0 and this distance is z. So dv by dz will be x omega by z. Make sense? That means for every ring, the velocity gradient is different. Now, every ring is going with different velocity. So the viscous force on the ring right? The viscous force would be like this. will be eta, area will be 2 pi x dx, velocity gradient will be x omega by z. So torque on the ring will be x into the viscous force, distance into force. This will be 2 pi eta omega x cube dx by z. This will give you the torque on the disk, which is integral torque on the rings, which is 2 pi eta omega by z integral x cube dx from 0 to r. So the total torque on the disk will be pi eta omega by 2z r power 4. That means if you take a disk of double the radius, you need to apply 16 times more torque. It's a power 4 function. It is 16 times more difficult to rotate a disk of 2r compared to a disk of r. Now I know this is equal to I alpha. So this is pi eta omega r power 4 by 2z. I of the disk is mr square by 2. And this will be minus d omega by dt. Alpha is not constant, it's changing with omega. Why minus? Since omega is decreasing. Then if you take this here, d omega by omega, and shift everything that side, you will end up with minus pi eta r power 4 नहीं r square आएगा by mz dt. 2 will cancel, 1 r square will cancel. Pi eta r square by mz, perfect. Limits. This is initially omega naught, this is omega, this is going from 0 to t. This will be ln omega by omega naught is minus pi eta r square time by mz. We get omega is equal to omega naught e power minus pi eta r square time by mz. That's your answer, everyone. You have to integrate 2 times. The first integration with respect to position, second integration with respect to time. Check out the steps. In case of rotational mechanics, alpha was constant. So you never had a problem. You could directly write omega final is equal to omega initial plus alpha t. Here you can't do that. Any doubts on this? This is what I was saying. The problems are either easy like the first one, or all the problems are like this only. Involves a lot of integration. Any doubts on this? This is the second time you're saying this. You will again see something like this in electromagnetism, EMI. That comes quite late, but you'll see this disk rotating thing 3 times. Is this clear? Suppose the same question, if I change the diagram like this, can tell me what will change? Suppose we have a container here and you kept a disk inside here. And if you rotate this with omega, what is the difference? Now there will be 2 viscous forces, na? Liquid on the top, liquid at the bottom. So into 2 kar lena torque ka, bas. That is only difference. Suppose if I do like this, suppose I have a cone like this, and this is rotating with omega, and this is filled with liquid. This would be interesting. How will you do this? We will choose an element like this, isn't it? These are the strips. No? This is going with x omega, this is going with 0. Then you find the viscous force tangentially. So here radius is also changing. Then you find the torque and integrate. That would be a really good one. But idea is the same. It's an integration based thing. So you can frame questions like this also. Clear with this? Let's see one more. So we have a part of a cylindrical pipe. The length is L. Radius is R. A liquid is flowing inside. Viscosity is eta. Now tell me one thing, if there is a viscosity, meaning you need to apply some pressure to move the liquid. So P1 is the pressure and P2 is the pressure here. So P1 and P2 is the pressure across the pipe. So P1 minus P2 is the pressure difference across the pipe. Because there's a viscosity, you have to apply pressure difference or else the liquid won't flow. L is the length of the pipe, R is the radius of the pipe. Assume the flow is steady flow. Again, what do you mean by steady flow? Each layer is going with by itself. It's not mixing up with other layers. Right? We will prove now, Vihan. You're asking how is that parabola thing and all. Now we will get it. This is the proof actually why it's a parabola there. So the first question. Can you tell me where is the velocity of the liquid zero here? When the liquid is flowing from left to right, where is the velocity zero? Here, na? The outside, circumference. Mein. Remember, I just told you that. Center mein you're flowing the fastest and circumference mein you're flowing the slowest. So find the velocity of the layer. At a distance x from the axis. Second thing, then how much liquid is flowing through the pipe every second? Find the volume flow per second through the pipe. You can also ask, find the velocity gradient dv by dx. Actually, all are related. So be careful here. dv by dz is not equal to v2 minus v1 by z2 minus z1 here. This is a thick layer. If I don't mention thin layer, don't use it. But then again, mains level, they'll never ask you thick layer. So you can be clear with that. Think how will you proceed with this? I'll give you 2-3 minutes. Figure out the first part. Obviously, P1 is greater than P2. So P1 is pushing. The liquid is going from left to right. It's like your ketchup ka bottle. The ketchup is coming out the center one liquid is going faster, the edges are going slower. So every layer will have different velocity. Yeah, it looks like similar to heat flow cylinder, but उसमें क्या है ना, heat flow was same everywhere ना. Heat flow में heat was flowing at a same rate everywhere, isn't it? But यहाँ पे क्या हो रहा था? Here heat is water is flowing more, here it is flowing less, here it is less, it is zero here. तो ऐसा जा रहा है ना. So think of like this, Ansh. अगर सोचो velocity same everywhere, then what is volume flow? Area into velocity, right? But every point velocity is changing, so you can't use A into V directly. Let me give an idea. See, can you draw FBD of this thin cylinder and tell me what are the forces on this? Take a cylinder at a distance x like this. इसका FBD draw करो. Take a cylinder of thickness x and draw the FBD. Tell me what are all the forces acting on that. Start from there. See, if you draw this FBD here, this is radius x. So this side, the pressure is P1 into area. From this side, the pressure is pushing you back, P2 into area. And how is the viscous force here? The viscous force is actually acting on the surface like this, na? You know how? Imagine like this. If you're looking at my screen, right? Look at this thing. If the pen is in my hand like this, if I try to pull the pen out of my hand, how is the friction on the pen? Isn't it on the surface? If I catch like this and see, if I try to pull it out, how am I applying force on this thing? Where is the viscous force acting? It is on this entire surface area, isn't it? The cylinder. Is that making sense? The viscous force is acting on the cylindrical surface, the surface area. So this would be the F viscous, right? And now here one important thing, this thing actually has a zero acceleration. Why? Here it is in a steady flow, each layer has a constant velocity. Velocity is not same, but each layer has a constant velocity. The center layer is going with one speed, but it will never change with time. Therefore, acceleration of each layer is zero, meaning one layer is going with 10, another layer is going with 8, another layer is going with 2, but these speeds don't change with time. So acceleration of each layer is zero. So here, velocity of layers is different, but they don't change with time. Are you getting the difference? They change with position, but they don't change with time. And what is acceleration? dv by dt. Is that making sense? The center layer is going with 10, second layer is going with 8, next layer is going with 6. Okay. So each layer will have a different velocity, but the velocity of that layer will never change. Different, but they don't change with time. So therefore, there is no acceleration for this system. So don't get confused there. Velocity is changing with position, not with time. Don't change with time. Perfect. Therefore, the system is acceleration is zero. So the pressure difference must be P1 minus P2 pi x square is equal to the F viscous force. Delta P is normally P final minus P initial. It's just a mathematical convention. We take final minus initial. So this should be actually P2 minus P1. So this can be written as minus delta P pi x square. Viscous force will be eta. What is the surface area? 2 pi xl into dv by dx. This is the surface area in contact. So यहाँ से actually third question आ गया directly. So dv by dx, that is a velocity gradient, is minus delta p. Pi will cancel. One x also will cancel. Delta p x by 2 pi eta l. That's your velocity gradient, everyone. It's not a linear function. It is changing with position. It's not a constant. It's changing with x. You can integrate this. So we get dv is equal to minus delta p by 2 pi eta l x dx. What are the limits? Where is velocity zero? At x is equal to pi cut हो गया ना 2 eta l. X is equal to r पे v is zero. So be careful with the limits. Isn't it? Velocity at the circumference is zero. Not at the center. So limits will go from r to x. So this will be v is equal to minus delta p by 4 eta l x square minus r square. So we get velocities delta p r square minus x square by 4 eta l. There it's a parabolic function. The velocity is changing as an x square. It's not a linear variation. So this is what actually happens in a liquid at center. So if you want to find the maximum speed, At center x is equal to 0, the speed is maximum, which is delta p r square by 4 eta L. So there, this is how the liquid velocity goes. Have a look at the steps. So this is the proof actually why that shape is a parabola. Question still not over. Second part of the question is how much liquid is flowing through the pipe. If this is a velocity, so every point has a different velocity. Every point has a different area. Then how much velocity, how much liquid is flowing through this pipe every second? Try. I'll give you a minute more for that. We know from equation of continuity it is area into V, but A is not constant, V is not constant. So if you take this thin cross section here, so the liquid is flowing out with this cross section with a constant V, meaning speed is constant for that small section, right? So volume flow per second through this thin strip. Now, because V is constant for this thin strip, you can assume A into V. So thin cross section will be A into V. Area is 2 pi x, circumference into thickness, and velocity is this guy. Delta P r square minus x square by 4 eta L. So what's the total volume flow per second through the pipe? Integrate this. This will be delta P pi 2 eta L r square x dx minus x cube dx. Limits will go from 0 to 4. That would be r square by r power 4 by 2 minus r power 4 by 4. That's r power 4 by 4. So we get delta P pi r power 4 by 8 eta L. You should remember this result. So volume per second. This is a second result that we use. Poiseuille's equation. Delta P pi, I'll use small r power 4 by 8 eta L. So when you have viscosity, the amount of liquid that flows through the pipe will depend on the radius of the pipe, which is power 4. L is the length of the pipe. Delta P is the pressure difference across the pipe. So if you take longer pipes, you need to apply more pressure for the liquid to flow. If you have bigger radius, more liquid will flow. This is the proof for this. This can be also asked as an advanced paragraph. Even at a mains level, they can ask you this question itself directly. They have asked multiple times this question. In a Poiseuille's equation, there is a name for this. This is how you got that unit's Poiseuille's. Poiseuille's equation. This is a second concept. The question was like this. In Poiseuille's equation, which quantity has to be measured carefully to reduce the error? Which one should you measure carefully to reduce error? Pressure, radius, length. radius, na, power 4. So there's a, if you get more error, you get 4 delta R there. Clear with this? So that is there. So next class when we catch up, we're going to use this equation. We're going to solve problems. It will look kind of like conduction now, heat transfer, what we did. Remember heat transfer, we did resistances. We converted the rod into a resistor. So similarly, we can also do the same thing for a water pipe also. So we're going to do that part. And then we have something called Stokes law. So mostly next class, we should be able to wrap up the chapter. Like there's a small one. Okay, with that we'll wrap up for the day. So we have done with the fluid mechanics today. So do finish it off. You can start solving your material, whatever you're doing. And there's a test online this week till Saturday. So make sure to give it. So any doubts, anything, you can stay back and ask, or else you're free to leave. So take care, stay safe. I'll see you guys again next week at 5:30 on Tuesday.